Hello and thank you for watching this presentation. My name is David Barber and I'm presenting on behalf of my co-authors Robert Dixon, Susan Deeny and Pascal Steenbakkers. We're presenting the US, Australia, the UK and the Netherlands respectively, and we're all from Europe. Now, this presentation is titled Issues and Solutions for Compartments with Exposed Structural Mass Timber Elements, and provides a brief introduction to what we need to address as fire safety engineers when we're looking at exposed structural mass timber elements. So mass timber buildings are obviously becoming more globally prevalent, and as part of the construction boom in mass timber, we're seeing a lot more desire for the timber to be exposed. Obviously, there's a lot of solutions for low-rise buildings where, because typically most of these buildings don't require higher fire ratings or any fire ratings at all, the timber can be fully exposed. That same sort of solution is wanted for high-rise buildings as well, which is not unexpected, of course, given the fact that timber buildings are very different and the warmth of timber is something that owners and tenants obviously desire. With more glulam, LVL and CLT being used, the structural frame is obviously combustible, and the question is, how do we deal with that combustibility as part of a high-rise building, or in some ways as part of even a low-rise or medium-rise building? The issue we have to address is that as the fire grows and develops, the mass timber, where it is exposed, forms part of the fire and actually influences the fire because of the combustibility of the timber. And there is a natural sort of feedback mechanism between, as the fire develops, it consumes the timber and obviously changes the fire, and as more timber is consumed, that has an influence on both the growth and decay of the fire. Building codes typically require high-rise buildings to resist a fire through to decay, and that's something we need to design for timber structures, the same we do for concrete or steel. For high-rise buildings, we need to ensure that we have a fire that is predictable and that we can actually design for that. This image on the right shows 3 potential outcomes where we have exposed mass timber, and we have to ensure that we have, as I said, a predictable fire outcome. Curve number 3, as you can see there, is where we have large areas of mass timber and we're expecting a heat release rate which will grow, but unfortunately we probably don't get a decay period that is predictable, or we get a decay period that is very much extended. That is not an outcome that we want from a fire design point of view. Curve number 2 is one where we actually potentially get what we want. We actually get the growth and development, and we actually get a decay period, but due to uncertainties in the type of protection or the type of material, we actually get regrowth, and this is something which has been proven through fire testing, and something we do need to be very careful of as we design. And that regrowth can be through glue line integrity failure that can occur in certain types of cross-laminated timber where we have the char potentially falling away in quite excessive amounts, which means that we get the timber below that being exposed, and we actually get a regrowth in the fire. That will cause potentially compartment regrowth, which is something we want to avoid. The other sort of regrowth can occur through the actual non-combustible protection to the actual timber, either being designed to fall or fail part of the way through the fire, or actually not being potentially tested for the situation it is in, and we actually get the protection falling and failing, and that exposes the timber behind that again, in some ways releasing a lot of fuel which is available to the fire, and again getting a regrowth situation. What we want from our point of view is a fire which has a slow and steady decay. So curve number 1, which is very, as I said, very predictable, we can design for that, and we need to understand how that fire will grow and how it will actually be influenced by the value and the volume of exposed timber that is actually in that compartment. Certainly as part of that, we need to understand obviously the material and where that is, but obviously as the more timber that is exposed, the longer the actual duration of the fire, and obviously we need to ensure that we have a situation of a fire which is potentially growing and is not overwhelming the actually constructed fire resistance ratings in the actual building. So how do we address these exposed mass timber structures? Well, we need to understand that heat release curve and understand it from the start all the way through to the end, and that includes the growth, development, and importantly that decay phase. And the decay phase for mass timber is actually one of the most important parts of the actual heat release curve. We need to assess a range of design fires, that's standard fires, which we would typically use to ensure that we understand how they work with the materials that are being provided, because they will have fire resistance ratings that are graded and based on a standard fire. And also from an approval point of view, most approval authorities are always going to want building designed and understood on the basis of standard fires. But also we need to design for natural fires, fires which are determined by the amount of ventilation that's available, the amount of fuel that's available, and it obviously include this decay period as well. We also need to determine this process of the fire actually being influenced by the exposed timber and this iterative or feedback process, because where the timber is exposed, it does influence the fire, makes the timber potentially, the fire actually have a longer growth period, and by having a longer growth period potentially involves more of the timber being consumed. So the only way to assess this is through an iterative process. It cannot be done by a simple calculation method, because at every calculation step the timber will, as I said, influence the actual final outcome. The actual structural capacity of all these timber members is obviously determined by the char depth and what is the residual cross section, and that char depth is important to be understood, not just the depth but also the thermal penetration depth that sits behind it as well, and it's influenced by the received heat flux. So the higher the temperature in the compartment, the higher the char rate, and potentially the longer and deep the fire is, the deeper the char that will actually occur. So for us to assess the structural capacity, we need to understand the fire, we need to understand the feedback loop that's occurring, this iterative process of understanding how the fire will burn, to be able to then determine the actual final structural capacity of the member through that residual cross section, and also that thermal penetration depth as well. Some of the other issues which will play a role in this is the reliable encapsulation, and as I indicated earlier, we don't want a fire curve which decays and then potentially regrows. We need protective elements to the timber which stay in place for the full duration of the fire and prevent the timber actually being charred or actually performing part of the fire at any point during that fire decay period. These two images on the top here show two fire tests on two different products, both protective materials. The one on the left is showing failure of the protective material just after an hour or so of being exposed to a standard fire. The one on the right is the same time period, but the materials are physically in place and are not failing. And again, this is important for us to be able to determine how those materials have performed when exposed to a standard fire, to be able to ensure that they are staying in place when we are putting them in place in a building and relying them to protect the timber and potentially protect it forming part of the actual fuel of the fire. We need to understand obviously the amount of exposed timber and whether this will potentially prolong the fire and potentially overwhelm the designed fire ratings. And the best way to think of that is we have a certain amount of capacity in all those structural members, and we've got a certain amount of force which is applied in this case, which is the fire and the duration of the fire. We also need to understand how the aspects like variable ventilation and the CLT adhesive performance impacts on that fire decay period. And this photo set on the bottom here is showing how, for a compartment test where we've got an exposed CLT wall, we've got fire decay which is occurring just under 2 hours there, but actually as the glue line failure is starting to occur, we're getting regrowth in that fire, and actually we'll get regrowth which consumes most of that compartment due to that glue line integrity failure. So it is a real issue that we need to address. There is more research that's needed in this area. We've got some very good research that's ongoing. There's been some substantial amount of fire tests that have occurred, and those fire tests have been very informative for engineers and researchers looking at exposed mass timber. This graphic on the slide here shows all the fire tests that have actually occurred, and there's those light blue dots, and the triangles are certainly other non-combustible compartments where we've looked at fires which have included mass timber and understood how those actually burn and how they influence the fire. The problem is they are on very, very small compartments, and we are then potentially having to try and extrapolate those to compartments which have 2,000 or 3,000 square meters, and obviously that's a real issue, because simply foot, we can extrapolate those numbers to those sort of values. There is a significant issue there from a scaling point of view, and also very different fire behavior between smaller compartments where we get flashover and we get all the actual fuel actually being consumed, and then we have a decay period, which is really reliant on the timber exposed. Where we have larger compartments, we get a very different fire, which is very much more reliant on different parts of the ventilation and potentially fires that travel through the compartment. And we have a decay period, which is reliant not just on the timber exposed, but also the fuel that's available at the time as well, and the ventilation. So we have very different compartment behavior, and we don't have any tests on large compartments to be able to understand that fire behavior. So certainly a lot more is needed in this sort of area. There's also more research needed on how exposed timber can influence vertical fire spread as well. This is something that is important as we want to understand how fire spread occurs, not just within the building, potentially also externally as well. So again, some great research that has been going on at the moment. We're using a lot of that in the way we design and engineer our buildings. There is still gaps, and there is still more work needed in a number of specific areas. So thank you for your attention, and thank you for watching this presentation. Any questions, please don't hesitate to email myself or email any of the co-authors. As I said, a lot of interesting times ahead. Thank you, and enjoy the rest of this conference.